Luke, esteemed scientists at IMEC, industry colleagues and partners, and honored guests, I am delighted to address you at ITF World 2023. Today, the chip industry is the engine that powers nearly every other industry. IMEC has played an essential role in advancing this incredible field. Founded in 1984, during the dawn of personal computers, IMEC has helped transform Gordon Moore's observation of doubling chip density every 24 months into an industrial reality, enabling the transistor to shrink to the scale of DNA strands. NVIDIA owes its very existence to this work. IMEC's open innovation model allows the entire semiconductor ecosystem to collaborate in pre-competitive research, sharing the burden and risk associated with complex R&D. One remarkable example of IMEC's collaboration model is their partnership with ASML in demonstrating the feasibility of double patterning immersion lithography, and later in the productization of EUV lithography. ASML's EUV lithography system fires laser pulses at a drop of 50,000 times a second, vaporizing it into a plasma that emits 13.5 nanometer EUV light, nearly X-ray. Multi-layer mirrors then guide the light to the mask reticle, which takes advantage of interference patterns to produce features down to 3 nanometer. The wafer is positioned within 1/4 of a nanometer and adjusted 20,000 times a second to account for any vibration. ASML's EUV lithography system is a scientific and engineering marvel. Today, we can build 3 nanometer chips with features 100,000 times finer and processing capabilities millions of times more powerful than when my career began. The progress of semiconductors allowed us to invent the GPU and accelerated computing, which let us tackle problems that traditional computers can't handle, like computer graphics, scientific computing, artificial intelligence, and self-driving cars. So what lies ahead? We are experiencing 2 simultaneous platform transitions: accelerated computing and generative AI. For nearly 4 decades, the exponential performance increase of the CPU was the governing dynamics of the technology industry. CPU design has matured, and chip density scaling at ISO cost and transistor performance scaling at ISO power have decelerated. As a result, global demand for cloud computing is causing data center power consumption to skyrocket. Striving for net zero sustainability while supporting the invaluable benefits of computing requires a new approach. The industry has turned to accelerated computing and AI. NVIDIA pioneered accelerated computing, coupling the parallel processing GPUs to work in tandem with the CPU. By offloading and accelerating compute-intensive algorithms, NVIDIA routinely speeds up applications by 10 to 100 times, while reducing power and cost by an order of magnitude. Scientists use NVIDIA like a time machine, accelerating time to insights while expanding the scale of their simulations to explore complex systems such as climate change and human biology. Gamers use NVIDIA to run virtual world simulations. Data centers accelerate compute-intensive workloads to save money and reclaim power to sustain growth. Using NVIDIA Modulus, a physics-informed AI tool, Siemens Energy emulates its heat recovery steam generators and wind farms, achieving results 250 times faster than traditional methods. Lawrence Berkeley and Los Alamos National Labs use NVIDIA accelerated computing to process complex numerical simulations more than 20 times faster than CPUs, saving $350 million and nearly 200 gigawatt hours of energy each year. Accelerated computing is sustainable computing, Accelerated computing, unlike general-purpose computing, is domain-specific and requires full-stack engineering from chip architecture, algorithm acceleration libraries, and application re-engineering. Each field of computational science, physics, biology, chemistry, fluids, quantum, mathematics, finance, social sciences, graphics, and imaging, has algorithms that need to be refactored and accelerated. Methods like finite element, Navier-Stokes, and Smith-Waterman gene sequence alignment have been around for a while. Others are new and groundbreaking, like deep learning. A decade ago, in 2012, Alex Kershevsky, Ilya Sutskever, and Jeffrey Hinton won the ImageNet Visual Recognition Challenge by a vast margin. AlexNet, a deep neural network, was trained on two GeForce GTX 580 gaming GPUs. NVIDIA gaming GPUs were accessible and cost-effective supercomputers for Hinton's researchers to train deep learning models. The entirely computer-trained model stunned the computer vision and AI community by beating the painstakingly human-engineered best-known algorithms. AlexNet, meeting NVIDIA CUDA GPUs, ignited the Big Bang of modern AI. We recognized that deep learning was a fantastic computer vision algorithm, and much more. Deep learning is a whole new way of writing software. With novel and large enough model architectures, training data, and accelerated computing, we can create universal function approximators of any dimension and learn predictive models from data. Inspired by the possibilities of tackling previously impossible problems, we dedicated our entire company to pursuing deep learning and AI. Working with researchers across the industry, NVIDIA reinvented the entire computing stack. From the new Tensor Core GPUs, cuDNN neural network processing library, multi-GPU chip-to-chip NVLink, Mellanox InfiniBand with in-network processing, the DGX AI supercomputer, and optimizations for countless frameworks such as TensorFlow, PyTorch, MXNet, PaddlePaddle, Onyx, JAX, NVIDIA TensorRT, Triton, and much more. We reinvented computing for deep learning. The first wave of AI that focused on computer vision and speech recognition has achieved superhuman capabilities and has opened up multi-trillion-dollar opportunities in robotics, autonomous vehicles, and manufacturing. Advanced chip manufacturing requires over 1,000 steps, producing features the size of a biomolecule. To make chips with quadrillions of features, each step must be nearly perfect to yield any output. Sophisticated computational sciences are performed at every stage to compute the features to be patterned and to do defect detection for inline process control. Chip manufacturing is an ideal application for NVIDIA accelerated computing and AI. D2S and IMS nanofabrication build mask writers using E-beam to create photoresist patterns on a mask. NVIDIA GPUs do the pattern rendering and mask process correction. TSMC and KLA use EUV and DUV illumination for mask inspection. NVIDIA GPUs process classical physics modeling and deep learning to generate synthetic reference images and detect defects. KLA and AMAT use NVIDIA for their E-beam wafer inspection systems and for their optical wafer inspection systems, which detect defects smaller than the pixel. Amazing. The data rate is extremely high, at 40 gigapixels per second, to achieve this as part of process control. Recently, we announced that TSMC, ASML, Synopsys, and NVIDIA work together to accelerate computational lithography. As you know, computational lithography simulates Maxwell's equations of light, passing through optics and interacting with photoresists. It is a vital step in chip making and the largest computational workload in chip design and manufacturing, consuming tens of billions of CPU hours annually. Massive data centers run 24/7 to create reticles for new chips. We have already accelerated the processing by 50 times. Tens of thousands of CPU servers can be replaced by a few hundred NVIDIA DGX systems, reducing power and cost by an order of magnitude. The savings will reduce carbon emissions or enable new algorithms like ILT and AI necessary to push beyond 2 nanometer. I am thrilled to see NVIDIA accelerated computing and AI in service of the world's chip-making industry. NVIDIA relentlessly drove up the performance and scale of AI computing and drove down the cost of training large models. With each generation, AI researchers scale the size of models and the amount of training data. In the past decade, we've increased the scale of deep learning by 1,000,000x. And then ChatGPT arrived. The AI heard around the world. A new wave of AI is here. It's called generative AI. In the first wave, AI learned perception. Now, AI can understand and generate information. ChatGPT, a generative pre-trained transformer, is a large language model with hundreds of billions of parameters, trained on trillions of words and sentences. It has learned the representation of human language and can generate text. ChatGPT is revolutionary due to its ease of use and incredible capabilities. It's a glimpse into the future of computers that understand any programming language and perform a broad range of tasks. Already, over 1,000 generative AI startups are inventing new applications. Tab9, for example, is a contextual code assistant that helps complete lines of code or generate entire functions from a prompt description. It can program in multiple popular languages, from JavaScript and Python to Rust, Go, and Bash. Runway uses generative AI to create and edit images and videos. Its production quality is so impressive that several Oscar-nominated films have used it. With Runway's generative AI, anyone can tell stories through pictures and video. In silico medicine uses generative AI to create a candidate drug in 1/3 the time and 1/10 the cost of traditional methods, which usually take over 4 years and cost around $500 million. In silico medicine is used by over 20 pharmaceutical companies. The market impact of perception AI is already significant. The impact of generative AI will be much bigger. Every form of information will be understood and enhanced by generative AI, from human language, music, pictures, video, 3D, to genes, proteins, and chemicals. The content on 200 million websites will be personalized and generated by AI. Billions of customer service calls will be automated by AI. Generative AI will assist 25 million software developers and hundreds of millions of creators. The yield of the $250 billion annual drug discovery R&D will be turbocharged by generative AI. From the advent of personal computers to the internet, mobile and cloud computing, each wave has expanded the realm of computing. AI is a new wave of computing that requires no programming skills and uses plain human language to perform seemingly intelligent tasks. With AI, 8 billion people will have access to the instrument of knowledge that was previously limited to only a few million programmers. The remarkable ease of use allowed ChatGPT to reach over 100 million users in just a few months, making it the fastest growing application in history. The impact of generative AI is profound. And as we advance the capabilities of AI, we must also be mindful to put even more emphasis on advancing the safety of AI, utilizing technologies like guardrail to keep it within the boundaries of its intended application and using human feedback to properly align with our values. What is the next wave of AI? Embodied AI refers to intelligent systems that can understand, reason about, and interact with the physical world. Examples include robotics, autonomous vehicles, and even chatbots that are smarter because they understand the physical world. Let's take a look at VIMA, a multimodal embodied AI. VIMA can perform tasks from visual and text prompts, like rearrange objects to match this scene. It can learn concepts and act accordingly, such as, this is a widget, and that's a thing, and then put this widget in that thing. It can also learn from demonstrations and stay within specified boundaries. VIMA runs on NVIDIA AI, and its digital twin runs in NVIDIA Omniverse. Physics-informed AI can learn to emulate physics and make predictions that obey physical laws, such as the conservation of energy or mass. NVIDIA is building a digital twin of our planet called Earth 2, which will first predict the weather, then long-range weather, and eventually climate. Current numerical weather prediction models are time-consuming. NVIDIA's Earth 2 team has created ForecastNet, a physics AI model that emulates global weather patterns 50 to 100,000 times faster. ForecastNet runs on NVIDIA AI, and the Earth 2 digital twin runs in NVIDIA Omniverse. Fusion reactors essentially form a small star inside magnetic bottles. Researchers at UK's Atomic Energy Authority and the University of Manchester are creating a digital twin of their fusion reactor, using physics AI to emulate plasma physics and robotics to control the reactions and sustain the burning plasma. Scientists can explore hypotheses by testing them in the digital twin before activating the physical reactor, improving energy yield, predictive maintenance, and reducing downtime. The reactor plasma physics AI runs on NVIDIA AI, and its digital twin runs in NVIDIA Omniverse. I look forward to physics AI, robotics, and Omniverse digital twins helping to also advance the future of chip manufacturing. Thank you all for this opportunity to speak at ITF World 2023. You are driving advancements in the world's most important industry. These breakthroughs include gate-all-around and carbon nanotube transistors, beyond copper metal systems, backside power, high numerical aperture EUV, computational lithography with ILT and AI, 3D packaging, CPO integrated silicon photonics, and generative AI EDA technologies to explore the massive design space. The next decade in the chip industry is going to be incredible. We're counting on you.